We consider an example of a linear transformation and determine its image. So consider the next one. So t of x is a times x, where a is the given matrix. A is the 3 by 3 matrix, so t works on R3 to the R3, and a is given by half, half, 0, half, half, 0, and 0, 0, 1. Well, this is the matrix which corresponds to the orthogonal projection on the plane V, where V has general equation x equals y. So the first two coordinates are the same. So we can make a picture. So we draw the axis, x, y, and z axis, 3 axes in R3, x, y, and z. Then V is basically the plane that we will sketch in blue. So V is the plane through the z-axis, and we try to sketch all elements in our R3 with equal x and y coordinates. So we have the following. Here we're going to rewrite t of x. Since t of x is the matrix A, so half, half, 0, half, half, 0, 0, 0, 1, times the vector, now we're going to write its coordinates, x1, x2, and x3. And we're going to calculate this matrix vector product. So as the first coordinate, we get a half times x1 plus a half times x2 plus 0 x3. And the second coordinate is the same, of course, because the second row of the matrix is the same, and the last row is 0, 0, 1 times x equals x3. So we see here that actually when we take out the constants x1 plus x2, we get a vector half, half, 0 plus x3 times, so x3 is a scalar before the vector 0, 0, 1. So by varying the constants x1, x2, and x3, so basically by varying the vectors x in R3, we see that the image of t, which is by definition the image of A, is basically the span. Well, the span, what is the span? Well, all combinations of the vectors are half, half, 0, and 0, 0, 1. So we can build up our image of t by taking two vectors and consider all linear combinations of those. So again, look at the same example of G being the orthogonal projection R3 to R3 on a plane with equation V, x is y. So the first and the second coordinates are the same. So now we're going to determine the kernel of T, which is the same as the kernel of A. Well, what is its definition? So x belongs to the kernel of A if and only if A times x equals 0. So if you want to determine the kernel of A, this amounts to solving the homogeneous equations. Ax is 0. So we form the augmented matrix with A on the left side and the 0 vector on the right. And we use Gauss-Jordan elimination to arrive at a reduced row echelon form, which is in this case given by matrix 1, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0. So look at this cleaned up matrix, then you see that the second variable is actually the free variable. So we may freely choose x2, since x1 and x3 are associated with the pivot columns. So x2 is the free variable. So we take x2 being equal to t, where t is some arbitrary but fixed constant in R. Then x can be written, x in the kernel can be written as x1, x2, x3, and x1 is given by minus x2, so x1 equals minus t. x2 was t and x3 is 0. So if we write this, then we get t times the vector minus 1, 1, 0. So actually the kernel is formed by taking all these kind of combinations. So actually the kernel is the line through the origin with direction vector minus 1, 1, 0. So check. There's something particular about this direction vector, that actually this d serves as the normal for the plane V. So basically the kernel here is the orthogonal component, orthogonal to the image of the transformation T.